All right, so we're going to be working on Chapter 5, Lesson 7, Rational Exponents. So we're going to learn about writing expressions with rational exponents in radical form and vice versa. And we're going to learn how to simplify expressions in exponential form or radical form. How do rational exponents apply to astronomy? So in astronomers refer to the space around a planet where the planet's gravity is stronger than the sun's as the sphere of influence of the planet. The radius r of the sphere of influence is given by the formula r equals d times m sub p over m sub s to the 2/5 power, where m sub p is the mass of the planet and m sub s is the mass of the sun, and d is the distance between the planet and the sun. So it gives you a formula where you can figure out what the radius of that sphere of influence is. So rational exponents and radicals. So you know that squaring a number and taking the square root of a number are inverse operations of each other. But how would you evaluate an expression that contains a fractional exponent, just like the example we looked at, such as the one above, right? You can investigate such an expression by assuming that fractional exponents behave as integral exponents. So let's take a look at b to the 1/2 power to the second power, right? So if I'm squaring b to the 1/2 power, really that means b to the 1/2 power times b to the 1/2 power. And I know by my exponent rules, right, whenever I multiply two things with the same base, I can add up their exponents. So I know that 1/2 plus 1/2 is 1. That'd be b to the 1 power, or just b. So the key concept here, right, is that for any real number b and any positive integer n, where you have b to the power of 1 over n, that's equal to the nth root of b, except for when b is less than 0, right, when b is negative or n is even. So for example, if I had 8 to the power, right, to the exponent of 1/3, 8 to the 1/3 power, that's equal to the third root of 8, or the third root of 8 is equal to 2, right? So this idea here that you can take any fractional exponent and write it as a radical is the thing that we want to take away here. So let's look at a few of these. So I have a to the 1/4 power and x to the 1/5 power. So if I look at this one, right, a to the 1/4 power, if I use the key concept we just looked at, that's equivalent to the fourth root of a, right? So that definition that we just learned, right? And then same thing here, I have x to the 1/5 power. So that would be the fifth root of x. So let's look at it in exponential form, right? So here they're giving them to me as radicals, right? So the third root of y. Well, if I look at the third root of y, that would be, again, equivalent to a fractional exponent. That would be equivalent to y to the 1/3 power. Again, if I look at part b over here, this is the eighth root of c. So that's going to be equal to c to the 1/8 power. So again, we can, in example 1, we went from fractional exponents to radicals, and in example 2, we went from radicals to exponents. Many expressions with fractional exponents can be evaluated using the definition of b to the 1n, or the properties of powers. So let's look at some examples here where we're going to evaluate expressions with rational exponents. So 16 to the negative 1/4 power. So I'm going to show you two different methods. So let's look at method number 1. So 16 to the negative 1/4 power, well, remember that when it's a negative exponent, right, it is actually the reciprocal. So it's actually 1 over 16th to the positive 1/4 power. That's what that negative exponent does. And then now I have 1 over 16 to the 1/4 power, right? So I'm going to rewrite the fractional exponent as a radical. So 16 to the 1/4 power is really just the fourth root of 16, right? Those are equivalent to each other. And then in the next step, I can rewrite 16. I know that's 2 to the 4th power, right? 2 times 2 times 2 times 2 is 16, so that's 2 to the 4th power. And I know if I do the 4th root of 2 to the 4th power, that's just going to equal 2 there. So this was really equivalent to 1 over 2. So that's my simplified answer there. So again, I went from converting a fractional exponent into a radical, and then I went ahead and simplified that radical down to an integer, and that gave me my simplified answer. Let's look at a second method. So a second method would have been taking the original problem and go ahead and rewriting it using, well, I can rewrite 16 as 2 to the 4th power here. And then now I have 2 to the 4th power to the power of negative 1/4. And if you remember your rules of exponents, right, this is a power to a power. So I would multiply these exponents here. So that would give me 2 to the negative 1 power. And again, since it's a negative exponent, it would go down here. It would be the reciprocal, so it would be 1 over 2. Again, if you notice, it still gives me the same answer, just two different methods of approaching the problem. Let's look at another example here. So I have 243 to the power of 3 to the 5th power. So let's look at method 1. So I have 243 to the 3/5 power. That's equal to 243 to the 3rd power times 1/5, right? Because 3 times 1/5 is 3/5. So I'm just rewriting this fraction as 3/5 to 3 times 1/5, right? So there's still just the same exponent here. And then I can go ahead and bring that 3 inside of a parentheses, right? These will still mean the same thing, but now it's a power to a power. I'm kind of just taking what I've done before in reverse there. And because it is a power to a power, it would just mean that I would have multiplied these, right? So 243 to the 3rd power, and all of that is to the 1/5 power. So again, I know the 1/5 power could be written as the 5th root of 243 to the 3rd power there, right? Using that same rule that we've talked about before. And then in the next step, I know that I could go ahead and take 243, and that's really 3 to the 5th power there. So if I have 3 to the 5th power to the 3rd power, and all of that is, I'm taking the 5th root of it, right? And go ahead and break it apart. I have 3 to the 5th times 3 to the 5th times 3 to the 5th. And so what that's going to do is it's going to go ahead and I can take the 5th root of all of these, which would just simplify to 3 times 3 times 3. And I know 3 times 3 times 3 is equal to 27. So 27 would be my final simplified answer. Let's go ahead and look at a different method. What if at the very beginning I would have simplified 243 as 3 to the 5th power? Then I would have had 3 to the 5th power to the 3/5 power. And again, that would be a power to a power rule, right? Because I have an exponent to another exponent, so I could just multiply those exponents. So what is 5 times 3/5? Well, that would give me 3, right? Because 5 times 3/5 would actually be like 15/5 when 15 divided by 5 is 3. So it'd be 3 to the 3rd power. And 3 to the 3rd power would be 3 times 3 times 3, which is equal to 27. So again, I end up with the same answer. There are multiple methods for getting to the answer. Just making sure you're using your exponent rules and being able to get down to the simplified answer. So in example 3b, method 1 uses a combination of the definition of the exponent, right, b to the 1/n, and the property of powers rules. This example suggests the following general definition for rational exponents. For any non-zero real number b and any integer m and n, with n having to be greater than 1, b to the power of m over n is equal to the nth root of b to the m power, right, which is equal to the nth root of b to the power of m. Okay, so very similar to the the definition we learned before, but now it doesn't just have to be 1 over n, it could be any number over n, just knowing that the denominator in the exponent is your root, and the numerator in the exponent is the power of what you're taking the radical of. So again, if I had 8 to the 2/3 power, that would be equal to the third root of 8 squared, or equivalently could be the third root of 8 and all of that to the second power. These are all equivalent expressions. And of course, that all simplifies down to 4. Because the third root of 8 is 2, and 2 squared is 4. Or I could say 8 squared is 64, and the third root of 64 is 4. So in general, we define b to the mnth power as b to the 1 over nth power to the n power, or b to the nth power to the 1nth power. So now we can apply the definition all across the board now. So if I have b to the 1nth to the m, that's equivalent to the nth root of b to the and all to the power of m. Or if I have b to the nth power to the 1nth power, that's equal to the nth root of b to the nth power. Again, these all mean the same thing. There's just different ways of being able to apply it. The rational exponents with a numerator other than 1, right? So here I have dealing with a word problem here. So in weightlifting, the formula m equals 512 minus 146,230b to the power of negative 8/5 can be used to estimate the maximum total mass that a weightlifter of mass b kilograms can lift in 2 lifts, the snatch and the clean and jerk combined. So in part A, it says, according to the formula, what is the maximum amount that 2000 Olympic champion Zhuang Zhan of China can lift if he weighs 72 kilograms? And part B says, Zhuang Zhan's winning total in the 2000 Olympics was 367.50 kilograms. Compare this to the value predicted by the formula. So let's go ahead and take the formula and let's go ahead and input our data here. So again, here's the equation, right? The original formula. I'm going to put in B, right? Because B is the mass of the weightlifter. So he weighs 72 kilograms. So we put 72 in. And then we go ahead and simplify our, you can use a calculator, simplify it, right? So I would do 146,230 to the power, or sorry, times 72 to the power of negative 8/5. And I would do 512 minus that. And that would give me approximately 356 kilograms. And what he actually did in the Olympics was 367.50 kilograms. So if I compare these two now, the formula prediction is close to the actual weight, but slightly lower. It actually under-predicted how much he actually lifted in the Olympics. So all of the properties of powers you learned in Lesson 5.1 apply to rational exponents. When simplifying expressions containing rational exponents, leave the exponent in rational form rather than writing the expression as a radical. So to simplify each expression, you must write the expression with all positive exponents. Furthermore, any exponents in the denominator of a fraction must be positive integers, so it may be necessary to rationalize the denominator. So let's look at some examples. So I have x to the 1/5 power times x to the 7th power. And then for part B, I have y to the negative 3/4 power. So let's look at part A first. So if I look at part A, right, I know that I can use my rules of exponents. They have the same base, so I can go ahead and just add the exponents. I can add the exponent 1/5 plus 7/5, and that would give me 8/5. So that would be my simplified answer, x to the power of 8/5. And if I did want to write it as a radical, it would be the 5th root of x to the 8th power, right? So now I'm going to go ahead and look at B. So here I know that I have a negative exponent, so I have to write it as its reciprocal. So it's going to be 1 over y to the positive 3/4 power. And then I'm going to go ahead and multiply, because the only way I can't have a fractional exponent in the denominator of a fraction. So I need to make it into a whole number. Well, how do I make it into a whole number? by turning it into, by multiplying by y to the 1/4 power. Because when I multiply these together, I'm going to go ahead and add their exponents. Well, 3/4 plus 1/4 is going to give me 4/4, right? This will help me rationalize my denominator. It'll help me have no fractional exponents in the bottom, right? So I know that 4/4 is equal to 1, so that's really just going to give me y to the first power on bottom. And on top, I have y to the 1/4 power. And so this would be my simplified answer here. I no longer have negative exponents, and I no longer have any fractional exponents in the denominator. So when simplifying a radical expression, it's always use the smallest index possible, right? Index being the root, right? And using rational exponents makes this process easier, but the answer should be written in radical form. So sometimes you are asked to write things in radical form. So example number 6 wants us to simplify radical expressions. So right now they're asking us to simplify these 3 radical expressions. So let's go ahead and look at just A at first. So I have the 8th root of 81 over the 6th root of 3. So first thing I'm going to do is I'm going to rewrite these radicals as rational exponents, right? So I know this is the 8th root of 81, so that would be equal to the 81 to the 1/8 power. The 6th root of 3 is going to be equivalent to 3 to the 1/6 power. So now I've been able to write them with fractional exponents, right? So now I can go ahead and simplify. So 81 I know is 3 to the 4th power, right? So now that I've written this as 3 to the 4th power, and if you notice these 3's line up now I have a power to a power, right? So if I have a power to a power, I can go ahead and multiply these, right? 4 times 1/8 is going to give me 1/2. So now I have 3 to the 1/2 over 3 to the 1/6 power. Well, since they have the same base and I'm dividing, right, I can just go ahead and subtract their exponents. I can do 3 to the 1/2 minus 1/6 power. So 1/2 minus 1/6 is 1/3. Or, again, written in as a radical, right, just converting it over, 3 to the 1/3 power is just the 3rd root of 3. Remember, the denominator is the root, so it's 3 to the 1st power, right? So the 3rd root of 3 to the 1st power is just the 3rd root of 3. And so that would be my simplified answer there. Let's look at B now. So I have the 4th root of 9z squared. So again, we're going to go ahead and rewrite this as a fractional exponent, right? So the 4th root of 9z squared is going to be the 9z squared to the 1/4 power. And then looking at this, we can go ahead and break apart 9z squared to just 3 squared, right? Because that's what 9 is just 3 squared times z squared. And when I do that, then I can go ahead and use the power to power, right? So 3 squared times to the 1/4 power, I multiply those exponents, so 2 times 1/4. And z squared to the 1/4 power, again, power to power, multiply the exponents, 2 times 1/4. And so that's going to give me 3 to the 1/2 times z to the 1/2. And now I can go ahead and rewrite those exponents as radicals. So instead of being to the 1/2 power, it'll be the 2nd root or square root of 3 times the square root of z, right? And so since both of these are just square roots, they have the exact same root, I can just combine them and rewrite it as the square root of 3z, right? 3 times z. So that would be my final simplified answer there. Let's go ahead and take a look at C now. So I have m to the 1/2 power minus 1 over m to the 1/2 power plus 1. So this is going to be really similar to when we were simplifying radicals when they had conjugates, right? Because this is, in order for this to be simplified, I cannot have this fractional exponent in the denominator. So what I'm going to do is I'm going to multiply by the conjugate. What is the conjugate of m to the 1/2 plus 1? M to the 1/2 minus 1. Because when I multiply these, the conjugate will leave me with no fractional exponent, right? But I got to make sure that I multiply whatever I multiply on the bottom, I got to multiply on top because that's like multiplying by 1. So when I multiply that out, right, let's do the bottom first. So m to the 1/2 power times m to the 1/2 power is m to the first power because they have the same exponent. M to the 1/2 times -1, that's negative m to the 1/2. And then 1 times m to the 1/2 is positive m to the 1/2, and then 1 times -1 is -1. And then on top, same thing, m to the 1/2 times m to the 1/2 is m. -1 times m to the 1/2 is -1/2, m to the 1/2, and then negative, -1 times m1/2 is -1 m1/2 again, and then -1 times -1 is +1. So once I've multiplied all these out in the numerator and the denominator, then I can go ahead and simplify. And really where you're going to simplify are these middle terms. So minus m to the 1/2 minus m to the 1/2, that's going to become minus 2 m to the 1/2. And over here where I have minus m to the 1/2 plus m to the 1/2, that's going to zero out. So in the denominator, I have just m minus 1. In the numerator, I have m minus 2m to the 1/2 plus 1. And so that's going to be my simplified answer for C. So again, using that conjugate here, I was able to rationalize the denominator there, so I don't have any more fractional exponents. So that would be my final simplified answer. So in conclusion, just the concept summary here of expressions of the rational exponents. An expression with rational exponents is simplified when all of the following conditions are met. It has no negative exponents. It has no fractional exponents in the denominator. It is not a complex fraction. And the index of any remaining radical is the least number possible. So that is the key ideas when simplifying rational expressions of the rational exponents. Thank you guys for watching. Let me know if you guys have any questions.